Hello AP Chemistry and welcome to a little bit of weak acid and or weak base titration math. So here it says let's calculate the pH in the solution formed by adding 10 mils of this to 40 mils of that. So it doesn't say that it's a titration, right? But we are adding some strong species to a weak species, right? So it's the essence of a titration, okay? So let's go ahead and write our reaction. So we know that we have NaOH, and we know that we have our benzoic acid, right, which we're just going to call weak acid because I don't feel like writing that out. And then that's going to give us some NaA plus some H2O, yes? All right, so then, and by weak acid I do mean HA, obviously. Okay, so then let's talk about how much of each we have, right? So here, if we have 0.01 and that, it's going to be 0.00 5 moles of this, right? And for my weak acid, we have 0.04 times 0.0025, which should give us 0.01, I believe. Yeah. And then that, right? Which means that this is going to react completely. Yes, strong species react completely. Which means that we're going to lose 0.005 of this, right? And we're going to lose 0.005 of this. I should have said 0, right? And we're going to gain 0.005 of this, right? Which means that this is going to be 0, right? This is going to be 0.005, right? 0.005. Yes? Moles. So then, now we can take those and turn them into our concentrations, right? So it's going to be over 50, so 0.05 liters over 0.05 liters, right? And this gives us our respective concentrations for our HA and our A minus, yes? Which means that we have both species present in our systems, which means at this point, this goes back to that other thing we talked about, right? Wherein we have our Ka times my HA over my A minus is equal to my H3O plus, right? So I know that Ka is 6.3 times 10 to the negative fifth, and I know that my HA, right, is going to be 0.005 over 0.05. I don't know why I wrote that way, capital M, and this is going to be 0.005 over 0.05. And what do we notice? Right, we notice that these are the same, right? Which means that they cancel out, which means that this is my H3O plus concentration, and I would take the negative log of that to get my pH. Yes? Does that make sense? Okay, now, the reason that these are equal is because this represents the half neutralization point, yes? And why, before we started this, should we have been able to look at that and said, ooh, half neutralization? Right, because this is double the concentration, right? And half of half neutralization, yeah? Does that make sense? Which means that this would be half neutralization, yes? All right, hopefully that makes sense. All right, next up, let's change color. So here it says calculate the pH in the solution formed by adding 10 mils of 0.1 molar HCl to 20 mils of 0.1 molar ammonia. What do we notice? Right, we notice, ding, 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 we are also at the half neutralization point again. Now, here it's really important, right? The thing that we're adding to is ammonia, right? So if we take my HCl plus my NH3, right, and then we're going to form NH4 plus and some Cl minus, okay? And for my HCl, it says that we have 0.01 times 0.1, so 0.001 moles of this. And for my ammonia, we have 0.1 times 0.02, 0.02, what? 0.1 times 0.02 is 0.002 moles of this, right? We have 0 of that, which then again reacts completely, right? So we're going to lose that, gain that, right? So this is going to be 0, this is going to be 0.001, 0.001. So like I said, half neutralization, right? And it's going to be over our new volume, which is going to be 0.3 liters, right? And so this is our molarity of each, right? Now, really, really important, right? This is going to go back to this expression again, right? Ka times Ha over A minus is equal to H3O plus, right? Because we want to find the pH. What do we notice though? Right, this is a base. So here you have a couple of options to think about, right? So here we could just use this as written, right? Where in my HA, this would be HA, right? Again, this would be our HA, and this would be my A minus. And then we would just have to solve for the Ka, right? So we would need to know the Ka specifically of ammonium, and we could solve it for that way. Yeah, does that make sense? Right? Alternately, right, we could plug it into a Kb expression, right? We could say that Kb is equal to hydroxide ion, right, times my protonated base, right, over my original base, right? We could do this and we could solve for hydroxide and then relate that to hydronium and then relate that to pH. Yes? All are sound and logical ways to do this, right? If we're pressed for time, though, this really is the most direct route, right? So if we knew the Kb of this, for example, we could just use that in Kw to get our Ka value, right? And then just like I said, plug these in, and that's really the easiest and most direct way to do that. Okay, next up, calculate the pH at the equivalence point when 40 mils of that is titrated with 0.05 molar NaOH. So if we have 40 mils of this, right, now it doesn't need to tell us how much of that is being added, right? We know that we're at the equivalence point, right? Which means what? Right, which means there is neither any benzoic acid nor is there any sodium hydroxide. What there is, though, is a significant amount of ding, 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 benzoate ion. Specifically, right, 0.04 liters times point that, which again gives us our 0.01 moles of my benzoate ion, right? So 0.01 moles of my benzoate ion, and again, benzoate ion is the conjugate base, right? Which means that if I take my benzoate plus water, right, I'm going to make my protonated base, right, plus my hydroxide ion, yes? All right. So then, here is where it's basically just like we did in the previous chapter, right? Okay, so here is where, so we have our 0.01 moles over, we're going to have 40 mils of this, and since this is double the concentration, we'll need 20 mils of that, so over a total of 0.6 liters, right? That's how much of that we have, right? And here it's just like before, right, where we have 0 and 0, and then we're going to have minus x plus x plus x, right? And so we're going to have this, right, so 0.01 divided by 0.6 minus x plus x plus x, and I'm going to set that equal to my K expression. Now, really important, this is the Ka of benzoic acid. If I'm talking about the benzoate ion, what do I need to solve for? Right, I'm going to solve for my Kb, and I'm going to set this up, yeah? So my Kb is going to equal to x squared over 0.01 over 0.6 minus x. Yes? And then I'll solve for my x, and my x will give me, right, my hydroxide ion concentration, which then via Kw I will relate to my hydronium ion concentration, which I can then use to get the pH. Yes? All right. Fantastic. Thank you for listening. Be good, and I will see you soon. Bye.